Imagine trying to solve a puzzle where every single move instantly triggers thousands of overlapping rules. You place a piece, and immediately, entire sections of the board become restricted. This is the core challenge of the n-queen problem, a classic benchmark in algorithm design. To understand how to solve it, we have to establish the physical constraints of our environment. We start with a standard chessboard, 8 rows by 8 columns. This gives us exactly 64 distinct squares to work with. Our piece is the queen. In chess, it is the most mobile unit on the board. Place one in the center, and it immediately projects power horizontally, controlling that entire row. It also projects power vertically, taking over the corresponding column. And most crucially, it strikes out in all diagonal directions. A single queen dictates the status of a massive portion of the board at once. The goal is to place 8 queens on this board without any of them attacking each other. Because each queen commands so much territory, randomly guessing the arrangement across 64 squares generates millions of doomed combinations. A blind trial-and-error approach will fail. Mathematicians eventually realize the logic required to solve this doesn't depend on the number 8. The rules remain the same whether you use 10, 20, or an arbitrary number, n, queens, on an n by n grid. To actually build the algorithm from scratch, we will isolate the variables. We will scale our environment down to n equals 4, giving us 4 queens on a 4 by 4 grid. Before writing a single line of code, we have to teach the computer how to evaluate its environment. It needs to recognize a safe position, a square where a newly placed queen is entirely outside the attack vectors of any piece already on the board. Conversely, it must immediately identify an unsafe position, any square that falls into an existing line of fire. To sort the safe squares from the unsafe ones, our algorithm needs a strict mathematical test. Every time the algorithm tries to place a queen, that placement must survive 3 distinct tests. If it fails even one, the position is rejected. The first test checks the horizontal axis. If a new piece drops into the same row as an existing queen, it fails. The second test checks the vertical axis. If it shares a column, it is immediately rejected. The final test computes the angles to verify if the new piece intercepts a diagonal path. If it does, it fails. You can track these conditions using 3 letters, R, C, D. R stands for absolute row safety, C guarantees column safety, and D enforces diagonal safety. The algorithm evaluates R, C, and D simultaneously. Only when a square passes all 3 can the computer lock in a queen and advance to the next step. Let's run the logic manually. We place our first queen in row 1, column 1. The board is empty, so R, C, and D pass instantly. We move down to row 2. The first square violates the column constraint, unsafe. We shift to the second square. This one fails the diagonal check, unsafe. The third square passes. The algorithm locks the second queen into row 2, column 3. Now we attempt row 3.
Column 1 is under a direct vertical attack. Column 2 is attacked diagonally. Column 3, vertically. Column 4, diagonally. We have hit a mathematical wall. There is no safe square anywhere in row 3. If a naive program reaches this point, it crashes or gets stuck in an infinite loop. We need an escape mechanism. We need backtracking. Instead of wiping the entire board clean and starting over, the algorithm simply steps backward. It removes the previous valid queen. Then it tests the next available safe square in that row. Here it finds row 2, column 4. This is a continuous logic loop. Place a queen, check if it's safe, go to the next row. If you hit a dead end, backtrack and try again. By stepping backward the moment it runs out of options, the algorithm guarantees it will exhaust every possibility without repeating its mistakes. To program this efficiently, we have to map out how the computer organizes these shifting choices. We model its decision-making process using a structure called a state space tree.
Every node on this tree is a snapshot of the board at a specific moment in time. The first 4 nodes represent the 4 possible column choices in row 1. Selecting a node commits a queen to a square, which then creates a new set of branches for the next row down. But remember what happens when the computer evaluates an unsafe position. This leads us to a process known as pruning. The instant a placement violates the R, C, or D constraints, the algorithm physically severs that branch of the tree. The computer will never calculate the rows beneath that severed branch. It completely ignores millions of permutations that branch would have eventually generated. If you are assigning seats to 4 people, and you know person A and person B refuse to sit together, you don't bother assigning the rest of the seats. You rearrange A and B immediately. By combining backtracking with aggressive pruning, the algorithm bypasses brute force entirely. It navigates massive sets of data surgically, only spending computational power on paths that have a chance of survival. The algorithm systematically navigates the tree, slicing away dead ends, stepping back when blocked, and locking in safe positions. Arriving at a terminal node outputs a perfect, valid arrangement. Every piece is secure on the horizontal, vertical, and diagonal axes. This brings us back to the formal definition you will encounter in exams. The n-queen problem requires placing n queens on an n by n chessboard, such that no 2 queens attack each other. We map out every potential sequence using a state space tree. We immediately halt the exploration of invalid placements using pruning, and we string it all together using backtracking, which gives our program the exact logic required to test a path, recognize failure, and gracefully retreat to try another option. With the mathematical model firmly established, we can take this theoretical blueprint and write the code. In the next part, we will translate this logic into a fully functional recursive algorithm.